focus for the past few days has been on EVT, which is finding an extreme value. The extreme value theorem says that if you have a closed interval and it is continuous and differentiable on that entire closed interval, then you are guaranteed one absolute max and one absolute min. What we're going to push towards is how do we find those local max and mins that are not guaranteed because EVT does not apply. So how do we determine if something's a repeated root and we find it as a critical point, but that critical point isn't an extrema? And that's kind of how we ended class yesterday, is we had the critical point value, and it was a repeated root, and it was not an extrema because the signs weren't changing on both sides of the graph. So in order to be successful in 4.3 and how the derivative affects the shape of the graph, I highly suggest keeping on a sheet of paper near you or around you, or having it at the front of your binder, the table I gave you that has F, F prime, and F double prime. So I have note cards if you want a note card, and I have just a blank sheet of paper if you want that. So does anybody need a note card that wants it? Because if you have that chart near you, it is going to make this unit so much easier. Okay. Okay. So, essentially what we are going to do, I'm going to write it on this so you guys watching can see, is we're going to construct that chart so that we can follow it and follow along with it. So the chart consists of F, F prime, and F double prime. Today our focus is going to be on the first derivative test, so we're really only looking at F and F prime, but for the sake of filling out the chart, we're going to put all three. So we have increasing, decreasing, and extrema. Again, like I said, we've been focusing on EVT this week, which is the extreme value theorem, and our goal has been to find the extrema. We've determined that extrema occur when the derivative is a critical point. A critical point is when the derivative is 0 or DNE. So, in order for a derivative to be 0, it has to cross or hit the x-axis. So in order for a critical point to be an extrema, we have to have what we call a change of sign. So we need the derivative to go from positive to negative or negative to positive. And that's going to occur if the graph goes from increasing to decreasing or decreasing to increasing. Similarly, we're going to talk about something called the second derivative test. The second derivative test is going to look at the second derivative and these same features. So the increase, decrease, and extrema repeat in F prime. And then the positive, the negative, the 0 DNE, where you have to have a change of sign, also repeats. Now, on the original function, we have for an increasing derivative, the original will be concave up. If it's decreasing, the original is concave down. And then if there's an extrema, you have a POI. And we put the extra P in there because, again, it's that possible POI. It can only be a POI if this and that occur. So it's a possible POI when you have an extrema. Again, we've used this chart before. This is just reiterating kind of what we already know and something to use and reference as we work through the problems. So what we have in 4.3 is something called the first derivative test. So the first derivative test is essentially going to be doing what we just talked about with the f's and the f primes. We're going to find our derivative. We're going to find the critical points of that derivative. And then we're going to determine if those critical points are maxes or mins using a sign chart test. So again, not all critical points are extrema. We saw that yesterday in the last example we looked at. It was in our one homework problem. So we're going to now have a test in which it tells us, okay, is this a critical point or not? And that test is called the first derivative test. So you're given the graph of the function f. So we know just looking at this graph, what type of function is this? Cubic, right? It's got 3 zeros, 2 extrema. So we can tell just from looking at it that this is a cubic. Cubic functions are odd in end behavior, meaning that they go in opposite directions. And we can look at this and we can say, okay, since it's an odd function, we know it can't have any absolute extrema. So this point here is what we call a relative max. And the word relative or local means that it's a maximum for what's around it. So if you look and if you just zoomed in here, yeah, okay, it would be a maximum for that area. And then down here we have, again, you could call it a local or a relative min. So part 1 is done. It said given the graph below, label those extrema. Now what we want to do is sketch the derivative based on that original. So the relative max appears to be about 1.2, let's say. So that rel max was at x equals 1.2. So what that means is an f prime of x, when x is 1.2, your y value needs to be what? So if you have a relative max on the original, the derivative at that value needs to be 0, because that is the slope of a horizontal tangent. So essentially, maximums and minimums are horizontal tangents, and the slope of a horizontal tangent is 0, because the slope of a horizontal line is 0. So 1.2, we plot our 0. The second relative extrema is our min, and it was at like x equals 4.6-ish. So now, in order to sketch the remainder of this curve, we know the zeros, but we have to talk about, okay, if f is increasing before x equals 1.2, f prime is what? Positive or negative? positive. The original is increasing, the derivative is positive. We can also say that f is concave down from where to where? Where does that graph appear to be concave down? From negative infinity to about 3. So if a graph changes from concave down to concave up, what does that make 3? Well, it makes 3 a POI on F, which makes it an extrema on F prime. So that means that between these two, at 3, I need to have a low point. We don't know where, so we're just going to make it the lowest point we have. After our extrema at 1.2, the graph decreases till 4.6. So F is decreasing from 1.2 to 4.6, which means F prime is negative. So what you will see is you have a positive till 1.2. It goes negative from 1.2 to 4.6. And then at 4.6, this graph, F begins to increase, which means F prime is positive once again. And it should logically make sense to me that the derivative of a cubic became a quadratic. Again, we graphed that using that chart and what we know. So, what I wanted you to notice, though, is what did we do here when we talked about F decreasing and F increasing? So when F, the original, changes from increasing to decreasing, my derivative changes from positive to negative. And that change occurs at 1.2. 1.2 is also a max. So a sign change on the derivative implies a maximum or a minimum on the original. And that's the first derivative test. So that's what, if you flip over and you look on the back, there's 1, 2, and 3. And it says if F prime changes from positive to negative, so that would be this case right here. F prime is changing from, right here, F prime changes from positive to negative, so that's the case we're talking about. Then F has a local max at that point of their change. And if you go back to your original graph, here's where it goes from increasing to decreasing. And what do we have on our graph? A max. If F prime changes from negative to positive, so negative to positive, then F has a local min at that set point. So again, going back to the original, decreasing to increasing, local min. If F prime does not change sign, then F does not have a maximum or a minimum. And that was the case with the problem in our textbook that was the 3x squared minus 6x plus 3. When you derived that and got your roots, you got x equals 1. and x equals 1 would not change signs. And that's what happened with the cubic at the end of the day yesterday. It went positive, positive. When we made that little sign chart, no sign change. It is important if you're asked to find an absolute maximum of a function on a closed interval, you must test the endpoints also. What theorem is this? EBT. So again, I'm just reiterating right here that EBT is not identical to this, but an extension of that. So that important theorem, that's EBT. It's saying if you're asked for absolute, then it has to be a closed interval and you have to check the endpoints. Because for whatever reason, we forget to check our endpoints. All right. So the original function is 3x to the fourth minus 4x cubed minus 12x squared plus 5. And it says find where the graph is increasing and decreasing. So the easiest way to go about doing that without a calculator is to determine where the derivative is positive or negative. So derivative of 3x to the fourth is 12x cubed. Derivative of 4x cubed is 12x squared. And derivative of 12x squared is 24x. So what's really nice about this is I can take out a 12x from each of those terms. And that leaves me with x squared minus x minus 2, which factors nicely. So you have 12x, x plus 1, x minus 2. And our roots, or our critical points as we call them, are 0, -1, +2. So what that means is these are the only 3 possible points on this function at which the graph could hit 0. So we're going to make what we call an f' sign line. And on that line, we're going to put our 3 critical points. And what we're going to do is determine the sign of those points. So the sign of those points is still coming from the derivative that's going to tell me stuff about the original. So I can't actually look at these 3 numbers because if I plug those 3 numbers in, I'm going to get 0. So what I want to do is look at something smaller than -1. So -2. Something between -1 and 0. So -0.5 is between 0 and 2, so 1, and bigger than 2, so 3. And what we're going to do is we're going to actually take these numbers and plug them in to the factored form, because we don't care about what the actual value is, we care about the sign. So if I take the number 2 and I plug it in right here with the 12x, a positive times a negative is going to give me a negative. So -2 plugged in out front is negative. Plug it in here. -2 plus 1 is going to be negative. A negative times a negative is a positive. So right now I have a positive number being multiplied here, -2 minus a -2 is going to be, so a positive times a negative is a, so what that means is everything to the left of -1 is negative. See, I don't care about the number. Okay, -1/2 plugged into the 12x. So positive times the negative is a -1/2 plus 1. Positive, right? Because -1/2 is smaller than 1. So I have a negative times a positive, which is a negative. -1/2 and -2 is going to be negative. So a negative times a negative is a okay, plug in 1, you get a positive. Plug in 1, you get a positive. Plug in 1, you get a negative. So negative, positive, positive is negative. Plug in 3, positive, 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 positive. So this represents the derivative. So go back to the chart I made you. If the derivative is negative, the original is decreasing. So what's really nice is if you kind of sketch in decreasing on that number line, and then you sketch in where it's positive increasing, and then where it's negative you do decreasing, and where it's positive you do increasing. Get the shape of the graph of the original. So what that means is if the derivative goes from negative to positive, you have a minimum. And what do those little dots kind of make? A minimum. So what we can say is that f decreases from -infinity to -1 and 0 to 2. F increases from -1 to 0 and 2 to infinity. The second part says identify the local max and local min. F has a local min at -1 and 2. And again, we can see that because they're the low parts on the sign chart. There is a max at 0. You're graphing it, aren't you? Yeah. All right, so obviously they're not all going to be polynomials. We're going to have some crazy gross math in there. That doesn't change the process. It's find your derivatives, find the critical points, make a sign test. So this is first times derivative of the second So that's a chain rule. So you have to take the outside derivative of the square root times the inside derivative, which is -2x. So first times derivative of the second plus second times derivative of the first. What's really nice about this is the 1/2 and the 2 cancel. So your derivative becomes x times x
So you get negative x squared all over the square root of 4 minus x squared plus the square root of 4 minus x squared.
So I like to just bring my fractions together. So what that means is that this piece here needs the square root of 4 minus x squared on top and bottom to have the same denominator. But when you multiply the square root of itself times itself, what's really nice is the square root goes away. So we end up getting negative x squared plus 4 minus x squared all over square root 4 minus x squared. And then when you're finding your critical points of any fraction, so you're finding the critical points of any fraction, f prime of 0 comes from the numerator, and f prime does not exist comes from the denominator. So we're going to set the numerator and denominator equal to 0 separately. So it changes and splits. So f prime of x equals 0 will come from, and again you can group that together, so you get negative 2x squared plus 4 equals 0. And f prime of x does not exist when your denominator equals 0. And both of these give the CPs. So over here you subtract your 2, or wow, you subtract your 4 and divide by negative 2. So you get x squared equals plus or minus the square root of 2. So x is plus or minus root 2. Over here, you'd square both sides, so you get 4 minus x squared equals 0. And then you'd get 4 equals x squared. So you get x equals plus or minus 2. So we have 4 critical points. Now, if you look at this original function, we know that under a square root can never be 0, or never be smaller than 0, rather. So the domain of this original function is negative 2 to 2, including 2, because it's not in the denominator. So you can have, if you plug in negative 2, you get 0. When you take it with the square root of 0 is 0, so that's valid. So when you do your sign test, we cannot find if to the left or to the right of the negative 2 and 2 is positive or negative, because there's nothing you can plug in. If I tried to plug in like negative 3 or positive 3, up here I'd get 4 minus 3 squared, so you get 4 minus 9, so that's a square root of a negative, and we know that's invalid. So you have to know your domain to know that you don't plug in around them. So the only possible extrema are going to be at the square roots. Because this isn't an EBT case, because we're only looking for the local, so we're not too concerned with the negative 2 and 2. So negative 2 and negative square root 2, to find a number between them is a little bit of a challenge, right? So we know that the square root of 4 is 2. So the square root of 2 has to be smaller than that, but we know it's also bigger than 1 because the square root of 1 is 1. So you're going to have to plug in something close to 2, maybe like 1.75.
so that you're safely far enough away from the square root of 2. So go back up, and it doesn't matter where you plug it in, but you need to plug that negative 1.75 in. So any negative number squared is positive. Any number under a square root has to be, the square root of any number is going to be positive. So the denominator is positive in this case no matter what. So it's really just concerning yourself with the numerator. So you have a negative and a negative, and the number we're squaring here, so it's like, that's really negative 2x squared plus 4. So if you square a number a little bit closer to 2, you're going to get a number a little bit smaller than 4. But if you multiply that number by 2, and it's negative, that's going to be bigger than 4, right? Because if you take 4 times 2, you get 8. Negative 8 would be bigger than 4. So this is going to be more negative than it is positive. So that means this is going to be negative in here. Does that kind of make sense? Without knowing it, I can figure that out. What's super nice is between the two is 0. 0 plugged in is super nice. So 0 plus 4 is positive. We know the bottom's positive. What's also really nice is this was a negative to start. So whether it was the negative 1.75 or the positive 1.75 that I plugged in, it's still going to be negative because the negative 2. Does that make sense? So this graph goes negative, positive, negative. So I have one local max, one local min, and f is decreasing from negative 2 to negative root 2 and root 2 to 2, and f is increasing from negative root 2 to root 2. Six problems. They don't take a ton of time, but they take enough time that I'd rather put in effort and get it good.